Now we're on 11D, moving right along. In the logistic models in previous lessons, we assumed a fixed carrying capacity for a population. Excuse me. However, other environmental factors may affect populations and prove to be more important. Part 1, or question 1, asks us, and then there we go with a crazy mark. Consider the hares and the lynxes in the article. Why did the logistic and exponential models fail? So you have an article from your preview, and you're pausing to give some answer here, and then come back. We'll look at the objectives and keep on going. A possible answer on question 1 could be that the population oscillates and therefore does not match an exponential or logistic model. The model fails because the effects of predation, something that is not reflected in either of those models. So when this lesson is over, we're going to understand that complex models, such as the predator-prey models, may be neither logistic nor exponential. The mathematical concepts of proportionality can be combined with other mathematical concepts to model complex behavior. So just kind of be aware, we're going to be looking at complex behaviors. You're going to be able to identify the constant of proportionality in a real-world scenario, that K, and we're going to develop a parameterized time series model with more than two dependent variables in a spreadsheet. Using the information from the article that we read in our preview, What Drives the 10-Year Cycle of Snowshoe Hares, we will develop a two-variable time series model to predict population size based on the current population size for two species that interact. Take time to read the article, to put some thought into our questions. And question 2 says, let's answer these questions based on the article. And so part A asks, is it reasonable to assume that the hare population never gets large enough that's going to lead to resource constraints? Put down your thoughts, yes, no, maybe. You could have possibly said something like, yes, that is an assumption that's reasonable. You might have said, no, never is a strong word. I think it is possible that the hare population could grow to a point where resources are strained. Move on and look at part B, which says, let's begin by investigating a simplified model for the hare population growth, assuming that the population never strains the available resources and that there are no predator lynxes. If there were 100 hares in the initial population and 102 hares at the end of the first month, then what is B, the hare population growth rate for the month? Okay, so we have 102 at the end of the month. There's a constant of proportionality times the 100 where we started, and if we divide both sides by that 100, we get that our constant proportionality is 1.02. So the growth rate, one way to look at this, the growth rate for the month is, well, 1 is where we started. The growth rate is going to actually be 2%, and a quick test would take our 100 where we started, multiply it by 0.02. We're going to get the 2, but we got to add it back to the 100, which is our whole. And yes, the 100 plus the 2 does get us where we landed, the 102. I'm looking for a letter. I thought they gave us a letter. B, the growth rate. So B, the growth rate, is 2%. Part C, write a general formula that determines the change in H, which is the number of hairs added to the population in 1 month if there were H hairs at the start of the month, and that the growth rate stays the same as part B. So the change, and if we go back up here and look at the simplified part where we started, the simplified part is right here. We ended up with 102. We have a constant proportionality. We have a starting number. And if you look at part, sorry, this is so far spread apart, I got to keep going back and forth. If you look at what they gave us to write a general formula on the change in H, what is it going to be for the change in H? Well, we had 2 is the change in H, but we're playing around with all of this information. How could we write the change in H with the growth rate with the number of, where is it? Hairs added to the population if there were H hairs at the start of the month. So if we have H at the start of the month, we're going to multiply this number, this B, whatever this constant of proportionality that we want to call it. And in this case, it's 0.02 times the number of hairs that are going to be, this is going to get us the number of hairs that are going to be added each month. This is a great time to hit pause and to study the things that we just talked about, wrote, scribbled, drew arrows. Make sure this makes sense before you go on to 3. Then go on to 3, try it by yourself first, and then I'll catch up with you in just a second. So, in question 2, we were looking at the hairs and the added population of the hairs. Question 3 says, now let's focus on the population of the lynxes. In the absence of food, the hairs, the lynx population is going to decay exponentially. If there were 100 lynxes in the initial population and 99 lynxes at the end of the first month, what is the M, the monthly mortality rate? So we can look at something like, we had 99 in the end. There's going to be a constant of proportionality where we had our 100. In other words, we ended up being a constant proportionality of 0.99. So we went down from our 100% or our 1, we went down 0.01. Our monthly mortality rate is, we're going down 1,000th. But then it asks us on part B to write a general formula that determines the change in L, which are the number of lynxes subtracted from the population in 1 month if there were L lynxes at the start of the month. That's what we were doing a while ago on the hairs. And the mortality rate stays the same. So our change in L, our change in L is that we're going to be going down 1/100th times all of the lynx population. Again, this is a great time for you to look at what we just calculated, played around with on question 3, and also what we calculated and played around with for the hairs on question 2, because when we get to question 4, it says so far. So far, we have a couple of exponential models, and as they stand, how accurate would they be for long-term predictions if the hairs and the lynxes did not interact? Put down some form, thoughts, answer. What you could put is that the hair model is unreasonable because the exponential population growth that we just had is not sustainable. And the lynx model is probably reasonable as it shows the lynx population declining. The population would eventually die out without food. As we continue to try to figure out what's going on with the predator-prey model, question 5 says, let's see what's going to happen. Let's see what's going to happen when the hares and lynxes interact. In particular, whenever they encounter each other, this is kind of funny, there is going to be a slight chance that a lynx is going to kill one of the hares, or 2 or 3, or however hungry they are feeling that day. Part A, if the number of hares increases, how is this going to affect the number of lynx-hare interactions? Okay, look at it again. If the number of hares increase, then how is this going to affect the number of lynx-hare interactions? Also, if the number of lynx increases, how in the world is that going to affect the number of the lynx-hare interactions? Jot down a thought. I have a thought. And possibly you might write that increasing either of the number of lynxes or hares really is going to result in more interactions. If we have more rabbits running around, if we have more of if we have more of the hares running around, there's more of a chance that the lynxes are going to be able to find more of them. If there are more lynxes running around, there's more of a chance that they're going to be able to find more of the hares, even if they're sparse. Part B. Assume that the number of kills, let's go ahead and give this a letter. Let's assume that the number of kills, which is a lynx killing a hare, is jointly proportional to both the number of hares, let's call that H, I know I'm real creative here, and the number of lynxes. So we're jointly proportional. The number of kills is jointly proportional to the number of hares and the number of lynxes using, sorry, I'm bouncing back and forth here, using K as the constant of proportionality to derive a formula in, we already have it, N for the number of kills in a month with the hares and the lynxes. So N, the number of kills, is jointly proportional to the number of hares and the number of lynxes. And I didn't write all the stuff down. Derive a formula for N with the number of kills in a month with H for hares and L for lynxes. And so we have something. We have the number of kills jointly proportional to hares and to lynxes. So I filled in some of the missing parts this time, so I'm not bouncing back and forth. And I brought our formula, our joint proportionality formula, from part B onto part C. We're going to keep going with trying to find this formula, and it says if there are 100 hares and 10 lynxes, there will be 2 kills in a month. Using the formula we developed in part B, right there, determine the value of K, the constant of proportionality. So if there are 2 kills in a month, K is equals to K times, and that says let's go ahead and let there be 100 hares and let there be 10 lynxes. So we're going to multiply the 10 and the 100 together, and then we're going to divide this off of both sides. And so K is going to be worth, I'll go ahead and grab a calculator. You can mess around with decimals. You can go ahead and divide it yourself. But 2 divided by 1,000 gets us a constant of proportionality of 2 thousandths. Part D asks us to go ahead and use the formula we got in part B and the value of K that we just found in part C. So here's the formula from part B. Write a general formula in for the number of kills in a month with H hairs and with L lynxes, and we're looking something like this. The number of kills is going to have a constant of proportionality of 2 thousandths times the number of lynxes times the number of hairs. We have a formula. But part 6, question 6 says, now let us derive a formula for the change in the hair population. Change in the hair population when the two populations are interacting. At the start of the month, we're going to have hares and lynxes, and the hares are going to reproduce just like they did in question 2. So I'm going to go back to question 2, and I'm going to find that the change in hares and their production is 0.02 times H. This is how many hares we are adding every month. But then it says, go on to describe the number of kills by the lynxes described in question 5, and what's going to be the change in the hare population. So maybe the straightforward one is we'll start with the number of hares being added, and then we're going to take this off right here. The number of kills, the number of hares dying. You don't have to use parentheses on this. I just like it. I think it looks better. This will be the number of hares that are being killed, that are disappearing. And so we have what it's asking for, the change in the hare population. Hang in there. Remember, it is often good to hit pause, soak this up, think about it, hit rewind, and go back and listen to these a little bit more. We just finished looking at the hare population, and now we're going to look at the lynx population when the two are interacting. So part A asks us to assume that the lynx population is going to require 20 kills to allow it to grow in size by one lynx. One growth, one up. In other words, for every one of these lynxes, we're going to need to have 20 kills to sustain the lynx population. And that pretty much answers part A, because it says what's the growth in this lynx population, and the growth is going to be the number of lynxes divided by 20 to increase the population. But it's going to take 20 hares dying for this growth. Part B says if at the start of the month you have this many hares and this many lynxes, and the lynxes die out, as in question 3, but are also growing by killing the hares as described right here in part 7a, what in the world is going to be the change in the lynx population? The change in the lynx population. From earlier in our notes, we know that the lynx population is dying out. But for it to grow, we need what we just discovered here to make it grow. Think on this, look on this. And part 7 and part 6, or questions number 6 and 7, can both be written in multitudinous ways. The equations that we have developed are going to be used in the spreadsheet template to be completed in practice 11D. And so I'm going to play around a little bit and just go ahead and tell you number of kills, the coefficient of determination is going to be multiplied, times the number of lynxes and the number of hares. And we had that coefficient of determination is 0.002 times L times the H. And this is the number of kills. The lynx growth, L-Y-N-X, growth. The growth is this formula, and the change in the lynx population is this formula. The last thing I want to do is to finish up with some notes in my lesson, and it talks about drawing a quick sketch of the hare population only with contrived time intervals, population numbers, and then discuss period and amplitude. So I need you to look at the graph. Notice it's starting at 2010, and then it goes up, looking here to 2011, then down at 2012. A couple of the questions are from first peak to the second peak. In other words, from up here at 2011 to over here at 2013, how many years? Well, to get from a bottom over to the next bottom, 2012 to 2010, 2 years. Or from a peak to a peak is 2013 to 2011. And so it asks us about the peak minus the valley. A peak at 100 and minus the valley, it's going to be an amplitude. In other words, we're up here at 100, we're down here at 20, and you'll see a formula. If we subtract the 100 minus 20 and cut it in half, we get that our amplitude is 40. In other words, sitting right here in the middle, we go up 40 and we go down 40. And this is an amplitude. It's the height divided by 2. It also mentions a little bit about peaks and valleys and the period. A period that we just said, and we didn't give it the name. It just says from peak to peak. But up here is the word period. And looking at the word period, that's going to be from a peak to a peak or a valley to a valley. And then the amplitude is where we took the numbers, the highest and the lowest, subtracted and divided by 2. So hit pause, get a couple of words off this page with period, peak to peak or valley to valley, and amplitude, where we take the height, the true height from top to bottom and divide by 2, or if you want to see it differently, we'll take the height number minus the bottom number and then divide by 2. Write these notes down for your homework, and this finishes lesson 11D. So if you have more, go look at the syllabus to find that out. Keep going, and if not, stop.